In this video lecture, we are going to discuss about the Lenz law of electromagnetic induction. In order to understand a Lenz law of electromagnetic induction, you need to understand some of the terms which are associated with Lenz law of electromagnetic inductions. These terms are the phenomenon of electromagnetic induction, magnetic flux, and Faraday law of Faraday's law of electromagnetic induction. So now let us explain these three terms one by one. Electromagnetic induction. Start from electromagnetic induction. What is electromagnetic induction? Whenever we move a bar magnet near a conductor, then an electromotive force is created in a conductor. And when EMF is generated, will cause generation of electric current. So such phenomenon is called electromagnetic induction. So in a simple word, if I explain an electromagnetic induction, whenever a bar magnet or any kind of magnet moves toward or whenever a bar magnet is basically moved near the conductor, then this bar magnet, basically the motion of the bar magnet causes a generation of an electromotive force. And generation of an electromotive force, you know that the electromotive force is a voltage, and the generation of electromotive force will result into an induction of an electric current. And such phenomenon with which a magnet, motion of a magnet cause a generation of induced electric current is known as an electromagnetic induction. Similarly, the term magnetic flux is defined as number of magnetic field of lines passing through a surface. Magnetic flux is represented by a symbol phi b, and it is equal to number of magnetic field of line B into A and area vector, and which can be rewritten as BA cos of theta. So now let us discuss Faraday law of electromagnetic induction. Faraday law of EMI. Faraday law of electromagnetic induction states that whenever we move a magnet near a conductor, whenever we move a magnet near a conductor, an induced EMF will be generated due to rate of change of magnetic flux. So we can write the Faraday law in form of equation that induced EMF is equal to rate of change of flux. However, there is a term minus used in Faraday law of electromagnetic induction. The term minus is basically used to indicate the direction of the electromotive force, and this direction of an electromotive force was explained by a law which is known as Lenz law of electromagnetic induction. So now let us explain the Lenz law of electromagnetic induction. Lenz law of electromagnetic induction states that whenever magnet is moved near a conductor, whenever a magnet move near a conductor, it will generate induced current through the conductor. Induced current through a conductor. Through a conductor. And this induced current in a conductor will produce its own magnetic field. And this created magnetic field, and this new created magnetic field will oppose the motion of magnet. So this is very important statement. It is quite simple in order to understand. This statement basically clearly states that if a magnet is moving near a conductor, when a magnet moves near a conductor, there will be a change in a magnetic flux. And when there is a change in a magnetic flux, a current will be induced in a conductor. So as you know that every moving charge, suppose we have a charge like electron and it is moving. So this moving charge have a current, and a charge having a current will also have a magnetic field, and a magnetic field will be perpendicular to the motion of the electric current or a charge. So now this means that whenever magnetic field is applied, there will magnetic field whenever a magnet is moved near a conducting coil, a current will be induced in a conducting coil, and this conducting induced current in a conducting coil will basically produce its own magnetic field, because the motion or in a wire, when a current is generated, it is basically a flow of the charges. So these current will also have a magnetic field component in it, and it will become perpendicular to the current. So this new created magnetic field will basically oppose the motion of the magnet, which is basically causing a generation of induced electric current in a wire. So let me explain Lenz law in a brief. Suppose that we have a conducting coil. This is a schematic representation of a conducting coil. And this conducting coil is connected with current detection device. It could be a galvanometer or ammeter. Suppose it is connected with a galvanometer. And we have a magnet. We have a magnet near this conducting wire. And since you know that magnet have two pole, one pole of the magnet is known as north pole, and other pole of the magnet is known as south pole. And you know that magnets have a magnetic field of line. These magnetic field of line are produced from north pole and they go toward the south pole like this. The magnetic field of line, basically they go toward the south pole inward like this. So now whenever this magnet move toward the inductor or toward the conducting coil, suppose that this a magnet have a velocity v and it is moving toward the conduction coil or toward the conductor. So this will, the motion of the magnet, as you know that magnet have a magnetic field of line, it will, the motion of magnet will basically cause a change in a flux, and rate of change in a flux will basically cause a generation of an electric current, induced electric current in the conducting wire. Initially, there will be a generation of electromotive force due to rate of change of flux, and the electromotive force will basically cause a generation of an induced electric current in a wire. Whenever a magnet moves toward the conductor or toward the conducting coil, so there will be a generation of an induced current, and the direction of induced current will be clockwise. clockwise. So we can represent the direction of a current clockwise as like this, this, this. So the induced current in a coil, this is the direction of coil. Induced current in a coil, induced current in a coil also generate its own magnetic field. And the direction of magnetic field will always be basically will change with the direction of induced current. So please keep in mind that the direction of induced current, basically the polarity of induced current, sometimes it will act as a south pole and sometimes the coil will act as a north pole. So the direction of the magnetism or magnetic field generated in a coil will depend on the motion of the bar magnet. So whenever bar magnet move toward the conducting coil, the direction of induced current will be clockwise, whereas the magnetic field generated in such coil by induced current, direction of the polarity of that magnetic field will be south. It will be south. So, dear student, as you know that like poles, let me clear it, sorry. Like poles, like poles, like poles repel each other. So whenever the magnet, in this case, when the magnet is moving toward the coil, so the coil become the magnetic field in a coil become as a it's become as a south pole. So the south pole of the coil, south pole of the coil will basically it will repel the south pole of the magnetic bar. So whenever magnet is moving toward the conductor, then in that case, in the conductor, there will be a generation of an induced current, and with induced current, there will be a magnetic field, and the magnetic field in a coil, the polarity of magnetic field in a coil will be act like a south pole, and the south pole of the magnet will basically this both the same poles, south and south pole of the magnet and magnetic coil will repel each other. Similarly, whenever this magnet is basically the bar magnet move backward or move away with a specific velocity from the conduction coil, this will basically cause a generation of a current in a coil, but in this situation, the generation of current will be anti-clockwise. And with anti-clockwise, the pole of the magnet will be changed into north pole. So in this situation, when a magnet move away from the magnetic coil with a certain velocity, from a conducting coil with a certain velocity, there will be an opposite there will be a generation of a there will be generation of induced current, but the direction of induced current will be anti-clockwise, and the pole or the polarity of this coil will be basically changed into a north pole, and in this case the magnetic coil will basically attract the bar magnet. So basically, we can say that the motion of a magnetic field, basically, or a magnetic bar with respect to a conducting coil, change magnetic polarity in a coil. So on the basis of this experimental observation, we can basically define Lenz law of electromagnetic induction. So Lenz law states that the direction of current induced in a conductor, direction of a current induced in a conductor, induced in a conductor by change in a magnetic field, by a change in a magnetic field, change in a magnetic field is such that the magnetic field created by the induced current, the magnetic field created by induced current induced current opposes the initial changing opposing oppose the initial changing magnetic field. So if I make the definition of Lenz law in a simple word, initially, whenever there is a bar magnet or any kind of magnet which move toward or away from the conductor, there will be a generation of an induced current in a conductor. And this induced current is basically produced due to a change in a magnetic field whenever the magnet move away or toward the conductor. So this induced current will also produce its own magnetic field. And this induced magnetic field have its own is induced due to an induced current. So the direction of the induced current will always be changed with the initial magnet, which is basically moving toward or away from the coil. So dear student, this is all about the Lenz law. Lenz law basically tells us about the direction of an induced current whenever a magnet moves toward or away from a conductor. So thank you for watching this lecture.